Welcome to Deep Dive. Today, we're plugging into something truly fundamental to modern life, the smart grid and the ongoing process of grid modernization.
Yeah, it's a huge topic.
It really is. This is a deep dive into how our electrical system is evolving, really trying to meet the demands of the 21st century.
That's right. We're going to unpack how we get power, how that system is changing, and why these shifts are so important for all of us. We've looked at everything from historical accounts to the latest research on grid tech.
Okay, let's start by picturing the traditional electrical grid. For decades, it's been this largely unseen network, right? Power plants generate electricity.
Mhm.
It travels in one direction across vast networks and eventually powers our homes and businesses. But this massive interconnected system had a starting point.
Indeed, the very first alternating current power grid system that actually began operating way back in 1886.
Wow, 1886?
Yeah, in Great Barrington, Massachusetts.
Mm.
Back then, it was a very centralized, unidirectional setup, designed simply to deliver power from one generating station to local users.
And then throughout the 20th century, these local grids started connecting, expanding.
Exactly, they grew and grew.
By the 1960s, we had these large, mature grid systems with massive central power stations, some reaching that, 1 to 3 gigawatt scale.
That's right. The thinking was bigger plants, more efficient, more cost-effective.
Yeah.
Economies of scale were really the key driver.
Makes sense.
Think about it, a massive boiler in a coal plant. It could operate at a much higher, more consistent temperature and pressure. Maximize that heat to electricity conversion.
But that also created potential issues. Right. Single points of failure, less adaptability.
Precisely. A system less adaptable to, changing demand patterns.
And this model, while it worked for a long time, it started to face challenges, especially from the, say, 70s through the 90s. I remember hearing more about blackouts, brownouts.
Exactly right. As electricity demand grew, really grew significantly,
Yeah.
the existing infrastructure sometimes just couldn't keep pace. That led to those power quality issues you mentioned.
Right.
And to handle peak demand, which might only be for a few hours a day, utilities had to fire up these less efficient, much more expensive peaking power generators.
Which ultimately bumps up costs for everyone.
Definitely increased electricity costs.
So, okay, this brings us to the smart grid. It's clearly more than just a minor upgrade. It sounds like a fundamental evolution. For our listeners, what exactly is a smart grid? What problems is it really designed to solve?
Okay, so a smart grid is basically an enhanced version of that traditional grid. It uses digital communications technology to monitor and react to changes in electricity usage in real time.
Real time is key.
Absolutely. It's designed to overcome those old limitations and, crucially, to seamlessly integrate new technologies and diverse energy sources. Think renewables, UVs.
So making the grid more flexible, more intelligent, more responsive.
That's the goal, responsive to our evolving energy needs.
Flexible. That seems like a really crucial aspect, especially when we think about how a smart grid manages energy flow. It's not just one way anymore.
Precisely. That's a huge shift. Traditional grids were engineered for that unidirectional flow, big central generators out to the users. But a smart grid is designed for bidirectional energy flows.
Two-way street.
Exactly. This is absolutely vital for integrating things like rooftop solar, where your home might generate power and send excess back to the grid.
Or electric vehicles, maybe. Charging and discharging.
Yes, EVs have that potential too, plus wind turbines, other distributed generation sources. They all feed into this two-way system.
Okay, but that reverse flow, that must have created some headaches for a system built for one-way traffic, right? Some technical hurdles.
Oh, it certainly can. Classic grids just weren't equipped to handle power coming from multiple directions.
Right.
That reverse flow could definitely cause safety and reliability issues if it's not managed properly.
So the smart grid has tech built in to handle that.
Yeah, it incorporates advanced technologies, sophisticated controls to navigate these situations, keep the grid stable.
Got it. And it's not just about where the power comes from, but also when and how much is used. I've heard about demand response.
Yes, demand response support is another really significant feature. Smart grids enable automated, real-time communication between the generators and the loads. That's us, the consumers.
Okay.
The main goal is to coordinate demand, essentially to smooth out those sharp peaks in electricity usage, flatten the curve, so to speak.
Right. So instead of utilities just having to build, extra power plants that sit idle most of the time, just waiting for those few peak hours,
Exactly.
the smart grid can somehow encourage or maybe even automatically adjust our usage during those critical times.
That's precisely it. By flattening those demand spikes, we can reduce the reliance on those expensive reserve or peaking generators.
Less wear and tear on equipment too, I imagine.
Definitely. Minimize wear and tear, potentially extend equipment life, and this is key for consumers potentially save money on energy bills by shifting usage patterns. The old system, with its one-way info flow, just lacked that dynamic interplay.
This all sounds incredibly complex, though. What are the actual core technologies that give a smart grid its intelligence? It's not just a software update, right?
Absolutely not. It's much deeper than that. Interestingly, many of the fundamental technologies are adaptations from other sectors. Think manufacturing, telecommunications, where they've been used for years.
Ah, okay. Like what?
Well, first, integrated communications is absolutely essential, foundational.
Okay.
This includes things like substation automation, those demand response systems we talked about,
Yeah.
distribution automation, SCADA, that's basically for remote monitoring and control of industrial gear,
Right, I've heard it's SCADA.
energy management systems, various communication networks like wireless mesh, power line carriers, fiber optics. It's a whole suite of comms tech.
So, establishing a really robust, reliable, two-way flow of information across the whole grid. That's the idea.
Exactly. This integrated communication infrastructure enables that real-time monitoring, controlled data exchange,
Mm.
all critical for optimizing reliability, asset use, and of course, security.
And then you need to actually see what's happening, right, in real time. That's
Mhm.
where sensing and measurement tech comes in.
Correct. These are like the eyes and ears of the smart grid. Their job, evaluating congestion, monitoring stability, tracking equipment health,
Even detecting energy theft.
yep, helping prevent energy theft, and providing crucial data to support all those control strategies.
So what kind of tech are we talking about here?
Things like advanced microprocessor meters, what we usually call smart meters,
Right.
wide area monitoring systems using phasor measurement units, or PMUs.
PMUs, those sound important.
They really are. Also distributed temperature sensing, real-time thermal rating systems, electromagnetic signature analysis, tools for time of use and real-time pricing, even advanced switches, cables, backscatter radio, digital protective relays. It's a lot.
You mentioned PMUs. I seem to recall reading they might have been critical in preventing or maybe lessening a major blackout.
Yes, it's a key point. Many experts in power systems believe the huge Northeast blackout of 2003.
Right, I remember that.
It could have been significantly contained, maybe even prevented from spreading so far, if a comprehensive wide-area phasor measurement network had been in place back then.
How so? What do they do?
PMUs provide these highly synchronized measurements of electrical conditions, voltage, current, frequency phase angles across a vast geographical area. It gives grid operators a much more detailed, real-time picture of the system's health and stability, far better than what they had before.
Wow. That's a pretty compelling what if. Okay, what other vital components make up this smart grid?
Another key technology is distributed power flow control. Think of these as devices you can clamp onto existing transmission lines.
Clamp on.
Yeah, strategically placed. And they can actively manage and direct the flow of power within those lines.
Oh.
This becomes especially important with more renewables coming online, wind and solar being variable. It allows for more precise, real-time control over where that energy goes. It helps the grid better utilize that intermittent energy by enabling more effective management and balancing of supply and demand moment to moment.
Interesting. So it's like having much finer control over the electricity superhighways. What about the actual power generation? Is that getting smarter too?
Absolutely. The concept of smart power generation involves using multiple, often identical generators that can start, stop, and operate efficiently at chosen output levels, independently.
More flexibility on the supply side.
Exactly. Making them well-suited for both base load and responding quickly to peak demands. Continuously matching generation with demand that's load balancing is fundamental for grid stability.
And that's getting harder with renewables, right? Because they're intermittent.
Considerably more challenging. With intermittent sources like wind and solar, other generators have to adjust their output much more dynamically, much more frequently to keep the grid balanced.
So you need that adaptability.
Precisely. In fact, Elring, the grid operator in Estonia, they actually ordered these specialized dynamic grid stability power plants specifically designed to rapidly compensate for sudden drops in supply. It highlights this growing need for agile generation.
And finally, power system automation. This sounds like the central nervous system coordinating everything.
You've got it. Power system automation enables rapid diagnosis and precise solutions for grid disruptions or outages. It sort of ties everything else together.
Okay.
There are three main tech categories here. Distributed intelligent agents, like localized controllers,
Mm-hmm.
sophisticated analytical tools, including AI algorithms and high-speed computing.
AI, really? In grid
Yeah.
management?
Oh, yes. And operational applications like SCADA and demand response systems.
That AI part sounds cutting edge. Are there examples of that actually happening?
There are. For instance, the Fujian power grid in China has implemented a wide area protection system that uses AI. It can quickly figure out the best control strategy during a disturbance and put it into action.
Wow. So it's really the combination, the synergy of all these technologies working together that defines the smartness of the grid. Quite a leap from 1886 Massachusetts.
It really is.
Yeah.
And this progress, developing and deploying these technologies, it hasn't just happened by itself. There have been major initiatives pushing it forward.
Like the U.S. Department of Energy's ARRA Smart Grid project. That was a big investment, wasn't it?
Huge. The American Recovery and Reinvestment Act of 2009 put over $9 billion combining public and private funds into smart grid tech.
9 billion.
Yeah. And it touched on pretty much everything we've discussed, deploying over 65 million smart meters, enhancing customer interfaces, automating distribution and substations, optimizing voltage.
VAR optimization, I think I saw that term.
Yes, volt VAR optimization. Also deploying synchrophasers, those PMUs we mentioned, enabling dynamic line rating, boosting cybersecurity, implementing advanced distribution management systems, investing in energy storage, better integrating renewables. It was comprehensive.
That is an incredibly broad scope. And it wasn't just about funding, right? There was also a big push for industry standards.
Absolutely critical. The National Institute of Standards and Technology, NIST, played a huge role there, identifying and establishing the necessary standards for smart grid implementation in the U.S.
Like what kind of standards?
They even included things like ITU-T-GHN, a standard for using home wiring for high-speed internet, potentially useful for smart home energy devices. And organizations like Oasis Energy Interop are developing XML standards for communication between energy management systems.
So getting everything to talk the same language, essentially.
Mhm.
Interoperability.
That's the goal. It's absolutely essential for the smart grid to reach its full potential.
But is there a catch?
Well, there's a potential challenge some have flagged. The growing number of patents, sometimes unrevealed patents covering various smart grid technologies,
Uh-oh.
could potentially undermine the benefits of standardization if patent holders decide to, assert their rights unexpectedly later on, after the tech is widespread.
Ah, the dreaded patent troll issue potential. Definitely something to watch. Okay, so we've talked about making the existing grid smarter, but there's also this growing concept of virtual power plants, or VPPs. How do they fit into this picture?
Virtual power plants, VPPs, are a really fascinating and I think increasingly vital part of the smart grid ecosystem. Think of them as coordinated collections of distributed energy resources, DRs.
DRs like what?
Things like rooftop solar panels, battery storage systems in homes and businesses, smart thermostats, even electric vehicles.
Yeah.
The key is that these individual spread out resources are intelligently coordinated.
Using software.
Yeah, using sophisticated software and communication tech to provide valuable services to the grid, acting much like a traditional centralized power plant would.
So it's like bundling up a whole bunch of smaller independent energy resources and managing them as if they were one big controllable power source.
Exactly that. And the need for VPPs is, frankly, becoming more and more urgent. We're seeing these growing near-term pressures on the U.S. grid.
Why? What's driving that?
Several things. The rapid expansion of AI data centers, they're power-hungry, new manufacturing initiatives coming online, and the accelerating electrification of transport and heating, all boosting overall electricity demand significantly.
So instead of just building more huge power plants, VPPs offer a way to tap into local resources and maybe make the grid more resilient.
Precisely.
Yeah.
Just recently, NRG Energy and Renew Home announced plans for a 1 gigawatt VPP in Texas using just smart thermostats.
1 gigawatt from thermostats.
Yeah, roughly the capacity of a dozen typical gas-fired peaker plants. It really shows the potential scale. And yes, they definitely improve grid reliability and resilience. Think backup power during emergencies using solar plus batteries or small generators. Duke Energy's microgrid projects are great examples of that localized reliability.
Okay, are there different ways these VPPs operate, different models?
Yeah, there are several distinct models emerging. One is the market participant VPP, where the VPP bids directly into wholesale electricity markets. Another model gaining traction is the utility-led aggregator-operated VPP. Here, the utility contracts with an aggregator.
A third party.
Right, who manages the collection of DERs and sells the grid services back to the utility through bilateral contracts. There are also utility-run and utility-operated VPPs, where the utility has more direct control. That utility-led model is interesting because it lets utilities directly leverage these distributed resources.
But I've heard scaling these VPPs up nationally can be tricky. What are the main roadblocks?
Yeah, a significant hurdle has been the lack of technology interoperability and consistent operational standards across different utility states and grid operators.
Patchwork quilt problem.
Exactly. It's often resulted in these bespoke VPP deployments, custom-built for each situation, which are difficult and costly to replicate and scale. VPP platform companies often have to customize their solutions for every single utility's protocols and state rules. Limits economies of scale.
So we need a more unified approach to really unlock VPP potential nationwide.
Definitely. And thankfully, there are increasing standardization efforts underway. DOE, industry stakeholders. They're trying to tackle this complexity, drive down costs. For example, the Collaborative Utility Solutions developed a functional DER registry model using a common information model. States and tribes can adopt it, reducing the need for everyone to reinvent the wheel.
Makes sense. And with all these connected devices, thermostats, batteries, EVs, cybersecurity must be a massive concern for VPPs.
Oh, absolutely paramount. The sheer number of connection points in the DERs making up a VPP dramatically expands the potential attack surface for, bad actors.
More doors to try and break down.
Pretty much. So robust cybersecurity strategies, data encryption, system governance, everything are absolutely essential for grid security and protecting customer data.
Beyond just providing extra power capacity when demand is high, what other services can VPPs offer the grid?
They're quite versatile. VPPs can provide a range of crucial grid services beyond just peak shaving. Things like energy provision, frequency response, helping keep the grids
At
balanced.
that 60 hertz frequency.
Exactly. And even black start capability.
Yeah.
That's the ability to help restart the grid after a major system-wide outage. It depends on the mix of DRs and the software controlling them, of course.
Okay. It's great to hear about the potential, but are there real-world examples, utility-led VPPs actually working now?
Yes, definitely. Several good ones. National Grid's Connected Solutions program in Massachusetts and New York that was deployed quickly and provides significant peak demand reduction.
Okay.
Green Mountain Power in Vermont has an innovative ESS leasing program focusing on residential batteries. And Rocky Mountain Power's WattSmart program in Utah is effectively using solar plus battery systems to provide more consistent or firm renewable power. So yeah, they're out there and working.
And what about government policy? Is it helping or hindering? Are there regulations or incentives supporting VPPs?
State regulatory and policy actions are definitely playing a crucial role. We're seeing more VPP deployments and more related policy initiatives at the state level.
Like what kind of policies?
Key areas include streamlining DR deployment, easier interconnection rules, financial incentives, developing clear frameworks for DR aggregation, and working to enable VPP participation in those wholesale electricity markets.
Ah, you mentioned wholesale markets. I heard about FRC Order 2222. That sounds like a big deal for VPPs wanting to play in that space.
It is potentially huge. Issued in 2020 by the Federal Energy Regulatory Commission, FRC Order 2222 basically mandates that the regional grid operators, the ISOs and RTOs,
Right.
they have to establish ways for aggregations of DRs to compete in their energy, capacity, and ancillary services markets. It could really unlock the economic value of DRs, especially in regions with restructured electricity markets.
But getting the customer energy data needed for that market participation sounds like another potential hurdle. How detailed does that data need to be?
That is a critical challenge. VPP aggregators often need pretty granular data, sometimes hourly, from utility meters, for things like establishing baseline usage, verifying performance, managing settlements.
Right.
But many utilities restrict third-party access to this data, often citing valid cybersecurity and customer privacy concerns, of course.
So the process to get the data is complicated?
It can be complex, time-consuming, creates uncertainty, hinders market participation. And interestingly, IFRC itself has said that customer usage data access is kind of outside its direct jurisdiction.
Well, it's left to
Individual ISOs, RTOs, states, tribes, or utilities to set the rules, leading to that fragmented landscape again.
So different regions are handling this data access issue differently.
Exactly. For example, NYSO in New York requires 6-second telemetry data for larger DRs in their markets. But PJM, covering the Mid-Atlantic,
Right.
They allow one-minute data scans for some resources
Yeah.
and even exempt smaller DERs from telemetry entirely. It's a real patchwork.
It also sounds important to make sure these VPP programs are inclusive, right? Not just benefiting big industrial customers.
Absolutely crucial. Strategies like prioritizing lower-cost DERs, think smart water heaters, like shifted energy is doing successfully in Hawaii, can help create more inclusive programs. Spreading the benefits.
And getting people to sign up. Enrollment.
Yeah, actively engaging and funding trusted community organizations, doing thoughtful outreach. That's key. The Mass Saves Community First Partnership is a good example. DOE is also launching initiatives to simplify enrollment prize challenges, technical assistance, resources for specific technologies.
And sometimes it's just about clear communication, making the benefits obvious.
Precisely. Minn Kota Power Cooperative's Demand Response Program has great enrollment, and they largely credit it to just clearly outlining the direct financial benefits to customers. Simple, concise communication works.
So, wow, we've journeyed from the historical roots of the grid all the way to smart grid tech and these innovative virtual power plants. It's clear the whole system is undergoing this profound transformation, really driven by digitalization.
That's really the big picture, isn't it? This increasing digitalization, with a smart grid as its foundation, it has the potential to fundamentally reshape electricity markets, blurring boundaries between energy sectors, adding huge flexibility.
And one area with massive potential impact seems to be how we consume electricity, this smart demand response idea.
Absolutely. Smart demand response could unlock tremendous system flexibility and significant cost savings. Imagine households, smart appliances, all intelligently adjusting consumption based on real-time grid conditions or prices. Billions of smart devices participating.
And this digitalization wave, it's not just electricity, right? It's hitting transport, buildings, industry.
Indeed. In transport, you've got real-time routing, EV battery checks, truck platooning,
Yeah.
shared mobility, all potentially boosting efficiency, though policy needs to steer it right.
And in our buildings, smart thermostats, smart lighting.
Huge potential savings there. Plus, smart lighting can do more, like indoor positioning or Li-Fi. And you see the growth of energy service companies, ESCOs, offering bundled energy management packages.
And industry. Smarter sensors, predictive maintenance.
Exactly. Advanced data analytics for complex decisions. Even things like 3D printing and aircraft manufacturing, saving materials, saving fuel. Data analytics for benchmarking energy use, moving towards autonomous control. It's transformative there, too.
Even on the supply side, oil and gas, power generation.
Yep. Digitalization helps increase resource recovery, improve production, cut costs, enhance safety, boost efficiency in power plants and distribution networks, reducing losses, extending infrastructure life.
And it feels like the falling costs of all this, tech smart meters, solar panels, batteries, sensors, is really helping accelerate this shift.
That's a crucial enabling factor, no doubt. These key components are getting cheaper and cheaper, making wider deployment much more economically feasible.
Of course, all this tech uses energy itself, right? Data centers, billions of connected devices, we can't ignore that footprint.
Very valid point. Global internet traffic, the number of connected devices, it's exploding. But there are significant efforts focused on improving data center efficiency. And policy around ICT energy use is becoming a much bigger global discussion.
And we also have to talk about the risks, don't we? Cybersecurity, privacy.
Absolutely critical. As energy systems get more connected, more digital, they inherently become more vulnerable to cyber threats. Robust security, building resilience. They're non-negotiable.
And privacy concerns, especially with smart meters in homes.
Yes, that needs careful handling. Well thought out policies, regulations to protect consumer data. Plus, we need to think about economic disruption jobs, skills needed for this new landscape.
So policy has this huge role to play in navigating the whole transformation, steering it towards goals like energy access, sustainability, security.
Definitely. And digital tools can even help make policy better. Better data collection, better analysis. Look at the UK's National Energy Efficiency Data Framework or data hubs in Nordic countries.
Are there countries really leaning into this?
Sure, China's using QR codes on energy labels to empower consumers. Singapore's building a comprehensive digital backbone, a data platform, investing in R&D, promoting open data, really leveraging digitalization in energy.
This has been an incredibly insightful deep dive. Smart grid, grid modernization. It's clearly such a dynamic field with potential to really reshape our energy system.
Indeed. From those core ideas of bidirectional flow and smart demand response, through all the enabling tech, to innovations like VPPs, the smart grid is a massive leap forward. towards a more flexible, reliable, efficient, and ultimately more sustainable energy future.
And it's clear that continued innovation, getting those standards right, and having supportive policies, they're all going to be absolutely essential to actually realize that potential.
Agreed. It's an ongoing journey, this modernization. And its impact, it's going to be profound on our daily lives on the planet.
So, maybe a final thought for everyone listening. Consider how this increasing intelligence, this interconnectedness of the energy grid, might reshape your relationship with energy consumption and production in the future. What role might you play in this evolving landscape?
It's a vital question, definitely something to mull over as we move towards this more digital, more electrified world.
Thank you again for tuning in. Until next time, stay curious.